My name is Yang Zhongqing. I am from Zhongqing University, and I'm first year of master. My professor is NTHU, and today I want to talk about a new method to constrain the Hubble constant with scattering in host galaxy of fast radio burst. So, what is the motivation? It is the Hubble constant is very important for astronomy. And why is it important? As we know, the university is expanding, and we want to know how fast it is. And Hubble's laws tell us how far from us, how fast it is. And it comes to the equation. Velocity equal Hubble constant times distance. So distance proportional 1 over Hubble constant. And however, there are 4 sigma difference between two methods. CMB and local distance ladder. And for CMB, it's about 68, and for the local distance ladder, it's about 74. So we want to find a new method to see which is correct. In the previous talk, my professor have introduced FRB. You guys already know it, so I want to introduce what is dispersion measure. DM is the electron density along the site. And easy to say, how many plasma in the unit distance? So the plasma be large, or the distance is large. The dm will be large. And when there is many plasma and radio go through, and it will cause the time delay be large. So dm proportional time delay and the amount of plasma and the distance. We always separate dm for 3 things. One is nearby Earth, Milky Way. We call dm Milky Way, and the other is nearby the FRB source, the host galaxies. We call dm host, and the other is between dm Milky Way and dm host. We call dm IGM. So they have the equation dm equal dm Milky Way plus dm IGM plus dm host. And from the group 2022, we have the equation dm IGM proportional 1 over Hubble constant. It is easy to imagine because dm has the information for the distance. So compared to the Hubble law, distance is proportional 1 over Hubble constant. So when we want to know the Hubble constant, we must know the 3 values. One is dm host, and dm Milky Way, and dm. For the dm, it's observable, so it's easy to get. And the dm Milky Way is nearby us. We can model it, so it's also easy to get. The difficult is to get the dm host value. In the previous work, we just assume a number, so it's difficult to have the clear value for the dm IGM. And there have a new method using scattering to measure the DM host. And what is scattering? It's the uniting the temporal scattering of FRB glasses due to the propagation effect through the host galaxy. The scattering is almost happened in the host galaxy. In the downside figure, we can see if the whole galaxy is surrounded by the plasma and the radial go through, it will cost more time to arrive the observer. So the plasma is large, the scattering will be large. It's very similar to the DM. And so scattering have the information DM host. How to calculate the scattering? We can see the up of the figure. There is a scattering tail, and the normal one, the fluency just comes down very fast, and because of the plasma, it will have the tail, so we can calculate the scattering. And let's have a small conclusion. We use observing scattering to get a better Hubble, DM host. And using the coordinates 2022, how to get it is very complex because of the time limit. I can't show now. You can ask me after talk. And then we get a better DMIGM. From the paper Group R 2022, DMIGM proportional 1 over Hubble constant, we get the better Hubble constant. We use the 9 FRB sample in our result. And this is what I use, 9 FRB. And this is the spec Z of observed redshift in 9 FRB. This 3 figure is the 3 sample of the FRB images. And comes to the result, how to optimize the Hubble constant. You see in the 2 figure, the X line is observed redshift, and the right line is modeled redshift, and with the scattering and DM derived. So observed redshift must be equal, the model redshift must be equal observed redshift. It comes to the red line. Z hat equals Z. And the model redshift including Hubble constant. So we set the Hubble constant as a parameter to see which Hubble constant let the data more close to the red line. In the right figure, we find when Hubble constant equals 55, let the data more close to the red line. We can compare to the Hubble constant equals 70 or 40. It's easy to see. It's more, the 55 is more close. Let's go back to the previous figure. 4 sigma difference between 2 methods. Now, in 2023, we have a new method to constrain the Hubble constant. We got the result, 55 plus minus 8, and it's below 62. It's close to the CMB. So our result is prefer CMB. What can we do in the future? we can increase the sample because that FRB is very less. And we can use burst telescope. And the left side of the figure shows where is the telescope in Taiwan. And the right-hand side shows that the telescope look like. Why we use this telescope? Because it can localize many FRBs to identify host galaxy with scattering. Easy to say, it's the best telescope for my work now. So, we have the conclusion. Hubble constant is one of the most important missions in astronomy. And DN is a new distance indicator to derive Hubble constant. We have a new method using scattering to measure DN host, and using model redshift with scattering to constrain the Hubble constant. Our result is 55 plus minus 8. And in the future, we can increase the sample or use the burst data to get the more correct value. Thank you.
Any questions from the audience?
Thank you for the talk. I only have one question. What's the distance for your source? I mean, distance between the source and yeah.
I really don't know. So.
Okay.
I have the redshift.
Yeah, redshift. Yeah.
Oh, redshift. You mean our calculation or the observe?
Your data.
Our data.
I see. I just see the data.
In this.
Oh, okay. Yeah.
Yes.
Okay. Yeah. Thank you.
Oh, I see.
Thanks for the interesting talk. So the value you had is smaller compared to the Planck one, which is, I think it's still smaller than the one accepted. So do you have any guess why this is? Is it because the dispersion measure along the line of sight is smaller than expected?
Yes, our work is smaller. I think because sample is very small, and we want to increase the sample feature, and we can use a better telescope to see if the answer will more close to the CMB, yes, to be large.
Okay.
Any more questions?
Thank you for your talk. So I would like to know, there are other different methods to calculate the H0. For example, using GW and the electromagnetic counterpart, and the results are around 72 to 73, something like that. So how would you compare your result to the existing methods that are already there? Because the value is pretty low, if I'm not wrong, from your results.
I think because we just find the method, so maybe after we do complicate, and we can see why they have different between the other methods.
Thank you.
Okay, we need to move to the next speaker. Let's thank speaker again. So our next speaker is